Maximum power theorem has a very huge engineering application, and even though it's very simple, its use is so large in engineering and other places that it's taught as a separate theorem. To state the theorem, we have a power supply V here and a source resistance Rs and a load resistance RL. The voltage and the source resistors are fixed, but you are allowed to change the value of RL, and you need to find out the value of RL where the power delivered to this load will be maximum. It turns out that the value of RL for which this power delivered will be maximum, it happens when RL is equal to RS. That is the simple power transfer theorem. For example, if you have an antenna as the load and you have a source with a given power supply and a given source resistance, then the load resistance must match the source resistance, or in that antenna domain we call it impedance, which will come later. But you need to maximize the power transfer to the antenna to get a maximum range for the transmitter. Let's derive the equation of the power transfer theorem. If we take this loop and we have a current I here, then we can apply Kirchoff voltage law in this loop that says V minus IRS minus IRL is equal to 0 for this loop. And from here we get I as, we take V on the these two terms here, and then we send RS plus RL on the other side, so we get V divided by RS plus RL. This is the current, and it will be same in RS as well RL, because they are in series. And from here we can find out, because this is also the current flowing in the IRL, so the power delivered to the load, let's call it PL, will be equal to this current flowing in this RL, which is same as I squared multiplied by RL. And we can substitute the value of this one from what we found here, is V square divided by RS plus RL whole squared multiplied by this load resistor RL. We can also write PL as V square divided by this thing, we can expand RS square plus RL square plus 2RS RL divided by RL, or V squared divided by RS square divided by RL plus RL plus 2RS. So this power can be maximum when this whole term is minimum. So the problem reduces to how to minimize this thing. So we can write this term, the condition for this to be minimum is that its differentiation with respect to the variable, we have kept RL as our variable, as the thing that we are trying to vary, and if we differentiate this whole thing with respect to RL, that will be the condition for the maxima or the minima. RS square divided by RL plus RL plus 2RS, that should be equal to 0. This implies differentiation of this term will be nx to the power n minus 1 becomes minus RS square divided by RL square. This is plus 1, and that RS we have kept the source resistor to be constant, so this differentiation becomes 0, and from here we get RS upon RL is equal whole square is equal to 1, and that will give us two values of RL divided by RL, either plus 1 or minus 1, and our resistances cannot be negative. So this implies the optimal condition for maxima or minima to be RL equal to RL. To show that this term is a minima, you will need to differentiate this term, this whole term again with respect to L, which will give you d2 over dL square of this whole term minus RS square divided by RL square plus 1 becomes RS square and 2RS square divided by RL cube, and this term is always positive, which means that our power delivered will be maximum when RS is equal to RL. With this, we can also try to find out what that value of this maximum power transfer will be. The max power transfer will be this value, what we call it PL, is equal to V square divided by, instead of RL we can write RS. So we have 2RS whole square, and here also we can write RS, which will be equal to V square divided by 4 times of RS square. So all you need to do is just this, find the V, what is V, and what is the source resistor. That will give you the value of the maximum power delivered, but that will be maximum only when you choose the right value of this load resistor. In engineering, what happens is this circuit that we have shown as a simplified voltage and RS, it's not like that. This can be a huge, very complicated circuit consisting of voltage sources, current sources, many resistors, many voltage sources. How do we solve that kind of problem for a maximum power transfer? And for this, we will try to do a couple of problems, rather just one problem, and then you can do that. Let us say we are given a circuit like this. We have a battery and a resistor, let's say, call it E1, this is R1, this is R2, this is E2, and these are delivered, this set of these things is delivering to a load RL, and or I will call here, we need to find out what is the value of RL that will lead to the maximum power transfer on RL. In order to do such kinds of the problem, and also we may be required to find what that maximum power will be. To do these kind of problem, what we do is this huge complicated circuit will be converted into its Thevenin's equivalent circuit, which looks like this. Any circuit like this can be replaced by a simplified circuit like this. All you need to find out is this load source resistor RL. We will call it here VR Thevenin resistor, and this is V Thevenin voltage. If we could find this RTH and VTH, we can find the value of RL, because RL will be nothing but this Thevenin resistor for the maximum power transfer. To find out the Thevenin resistor, Thevenin says replace all the voltage sources with short. So we replace E1 and E2 as short, then we get a circuit like this. This is R1, this is R1, and there was a voltage source that we replaced it with a short. These are the places we had voltages, and we have replaced this with short, and now we are trying to look the circuit from this point, trying to find out the equivalent resistance looking from this circuit. So that equivalent resistor is called R Thevenin, and in this case R Thevenin is the parallel of these two resistors, that will be equal to R1 R2 divided by R1 plus R2. So this circuit can be replaced by a circuit where this resistance R Thevenin is nothing but R1 R2 divided by R1 plus R2. So the first part of the question, that what is the value of RL for which this circuit will deliver the maximum power, is be the same as this series resistor, which is equal to R1 R2 divided by R1 plus R2. If you are required, I'll write it here. If you are required to find out what is the value of that maximum power, then you will also need to find out the Thevenin's voltage. The Thevenin's voltage can be found by opening this load resistor here and finding out the voltage appearing at this point. And we can find this using this E1 R1, this is E2 R1 R2, E1 E2, and we are trying to find out the voltage appearing between the points A and B. To do that, we set up a loop. Let us say a current I is flowing in this circuit. I current flows here, it goes here, and because this is an open circuit, this current cannot go over here, and that's why this whole current I is going to return to this loop and flowing like this. We can apply the Kirchoff voltage law in this loop. That will give us, let us say, E1 minus E2. I am doing two steps in one step. E1 minus E2 difference is trying to deliver this current, which will be equal to the IR drops in these resistors. That will be equal to I times of R1 plus I times of R2, which will give us I as E1 minus E2 divided by R1 plus R2. To find out the voltage of A with respect to 2, we can either take this particular branch or this branch and find out the voltage appearing between in these two branches will be E1 minus I1 R1. So VAB is nothing but E1 minus I1 I R1, and that will become equal to E1 minus I, we have found out from here, so E1 minus E2 multiplied by R1 divided by R1 plus R2. If we simplify this, we get E1 R1 minus E1 R1 cancels, E1 R2 here, E1 R2, and then this minus becomes plus E2 R1 plus E2 R1 divided by R1 plus R2, which is the symmetrical result. And this VAB is nothing but we have V or TH. And we know that the maximum power transfer P is nothing but, we had done it earlier, V square divided by 4RS. In our case, it becomes equal to this thing whole square, which is E1 R2 plus E2 R1 whole square divided by R1 plus R2 whole square multiplied by divided by RS. And in our case, we calculated that this was our source resistors, R1 R2 whole squared multiplied R1 plus R2 whole square, and this 4 here. That will give us, if we simplify this, there is no square here, but this square cancels to this one, becomes E1 R2 plus E2 R1 whole squared divided by 4 times of R1 R2 R1 plus R2 multiplied by R1 R2. This is our answer. just cross check it, make sure I am not doing any calculation mistakes. I hope I have not, but this is how you proceed to calculate the maximum power delivered in any load for a given complex source. The next thing that we would do is to extend this maximum power theorem for a complex load, because we talked about the antenna. Antenna are not simply load resistors, and the voltage driving to an antenna is not a simple DC volt. It's a complex time varying voltage